All right, so today our focus is on graphing two different shapes. We are graphing cardioids and limacons. All right, it looks like limacon. It is not limacons. It's French. I don't know how to make the cool French symbol on my notes here, but that's what it looks like. Anybody know what this is called? You're in French. It's got like a little tail. Kind of looks like an ear if it were on the bottom side of a C. I don't know. I don't speak French. If you want me to put a French accent on it today, I can. We can call it a Limassol. All right, so good. We're Limassons all day today. Kind of like croissants, only different. Here we go. So we're looking at these shapes. We've got cardioids, limacons without a loop and with a loop. They all have the same basic structure. It is some constant added or subtracted to sine and cosine. And the sine and cosine can have a leading coefficient. And depending on those numbers that are there are going to make the difference. And so if you add a constant to cosine with the same leading coefficient, it is going to get you a cardioid. It is this shape right here. Okay? A cardioid looks like a peach, we will say. All right? It's going to go around. Notice that it comes around. It's a circle. It's a little bit offset. And it goes back and touches the origin as we go through that. We can have a Limassol without a loop, okay? Without a loop. That's this thing right here, okay? This happens when the number that you're adding is bigger than the coefficient. If it's a bigger number, then it is going to get you this shape right here. To me, that shape is like if you ever played basketball and your basketball's been sitting outside in the cold and then you try to dribble it and it's just flat on one side, that's what happened here, okay? It's a cold basketball. No one else gets that reference, but in my brain, it makes a lot of sense. So just deal with that. All right. And then the last one here is a Limassol with a loop. If it's with a loop, the number we're adding is smaller than the other one. And so it gets you this shape, does this cool little loop-de-loop thing in the middle. Depending on the shape or the numbers, the size of the loop will get bigger or smaller, just depending. All right. That one's kind of the most difficult one to graph, but also the funnest one to graph as well. And so in order to graph these things, we want to talk about some basics. And we did this a little bit in Bell Work. We'll kind of go back and revisit it. And so the first thing we're going to do is just identify shapes. The first one says 3 plus 2 cosine theta. And so we're going to go through and just give this a label. What's my picture going to look like? If those two numbers are the same, it's a cardioid. They're not the same. A is bigger than B. The number we're adding is bigger than the other one. So it's a Limassol. With or without a loop? Without a loop. That's it. That's all we're doing here. Take a second with your neighbor and identify all 5 shapes. First one says 1 plus cosine theta. Kate, what do you think on 1 plus cosine theta? It's a cardioid. Those numbers are the same in front. They're both a coefficient of 1, so it's a cardioid. 4 minus 4 sine theta. Ashley, what do you think on that one? Cardioid. Same number, 4, cardioid. 2 minus cosine theta. Allison, what do you think on that one? Yep. Limassol without a loop. And then Audrey up here in front. 2 minus 5 sine theta. What do you think on that? Limassol with a loop. I even said in the front. I was trying to be good, but it was good. With a loop. You're good. It's because I struggle. Audrey, you're fine. It doesn't matter. You're both very into it. I don't care. Limassol with a loop. Again, the leading coefficient is different. Nothing tough about that. Identifying them are going to help you make a better picture as you go. Here we go. Second part here. Symmetry is important. We've talked about even and odd functions before. It's weird. Let's just do a sidetrack here. If we had a function that was even compared to odd, if we have an even function, we're talking about symmetry. Anybody remember what even means with symmetry? Show me with your hands. How would you fold something that had even symmetry? Even is this way. You're all doing the walrus clap. I appreciate that. That is y-axis symmetry. Even is y-axis. Odd would be origin symmetry. Think about those two, sine and cosine. One of them is even, and one of them is odd. Talk with your neighbor and remember which one's even, which one's odd. Think about what a sine or a cosine graph looks like. Show me with your fingers sine curves. If you have a sine curve, show me an even number if you think it's an even function. Show me an odd number if you think it's an odd function. What is a sine curve going to look like? We have forgotten. We had even and odd functions, but a sine curve is odd. If we graphed sine, where did we graph sine curves? Where did we start? Start in the middle, and we'd go top, middle, bottom, middle, top, and it would do this guy, and it would do this guy. This graph is odd. Cosine curves, on the other hand, cosine curves are going to be even because cosine curves start at the top, middle, bottom, middle, bottom. And that curve right there could be folded over that axis. We've done that before. That's great. It's a little bit more confusing with polar graphs because with polar graphs, it's a wheel. We are taking this thing and we are starting at 0 degrees and going all the way around to 360 degrees. Or starting at 0 and going to 2 pi. And so this idea of even and odd is tougher to understand. All right? The better way of understanding these things is thinking about a unit circle. So if I'm on a unit circle and I want to graph sine, okay, so now I'm on a wheel and I'm going 0 to 360 degrees. And I'm graphing sine. Which way would you fold this graph so that the sine value matches up with the exact same other sine value? Show me with your hands. How would you fold this up so that the sine values would fold and match up with the same one on the other side? Everybody's giving me this weird middle ground. The correct answer is over the y-axis. Right? Think about sine values. If I looked at a sine value on my graph, sine value right there is radical 3 over 2. And if I folded it straight across, it would also be radical 3 over 2. And down here, it's negative, and over there, it's negative. So when I fold them over, they would match up. They have symmetry. And so if I graph something that is a sine function on a polar graph, it's going to have y-axis symmetry. So if you're thinking of a shape, it would be a shape like a heart. I don't know why I'm not using pink if I'm going to graph a heart. Gee, that's so... Oh, it's Valentine's week. That's a pretty good heart right there. That's top-notch heart stuff right there. That's what a sine curve is going to look like. It's going to have y-axis symmetry. That's opposite if I were to do a cosine curve. If I were to start at 0 and go all the way around to 360 degrees, show me with your hand, how would you fold a cosine value on a unit circle so that it matches up with its partner cosine value? We would fold it down. When we think cosine, what letter do we think about? I was thinking more x, as in the x-axis, but the letter C also has x-axis symmetry. And so you could draw a picture of the letter C. Oh, that's a bad C. And you would notice that they would match up and have x-axis symmetry as you fold over that. And so there we go. We understand the basics of what's happening there. Everybody understand symmetry? Not super complicated. If it's sine, y-axis, cosine, x-axis. Let's find the maximum value. So again, this is what we did in Bellwork. A quick reminder of what we did in Bellwork. 3 plus 2 cosine theta. It's 3 plus 2 times something. I want to think about what number could go right here to make this as big as possible. Remember, Grant said that sine or cosine is going to live in the world of -1 to 1. And so if I want to find a maximum or a minimum, I'm basically just thinking, what number do I want to plug in, -1 or 1? For this problem right here, 3 plus 2 times something, what number would I want that to be, a 1 or a -1? A 1, because if it's at 1, it's 3 plus 2 And so you're going to have a maximum value that is equal to 5. No matter what number I plug in, I'm never going to get anything bigger than 1 for cosine. And so the biggest number I could possibly get is 5. It's a maximum of 5 at what angle is there going to be a maximum of 5? When is cosine going to get you 1? At 0 degrees. So I have a maximum of 5 at 0 degrees. For the next one, it's 2 minus something. I'm trying to figure out what number wants to go in those parentheses. What do I want cosine to be? It could either be -1, 0, or 1. What number is going to make it as big as possible? -1, because if I had a -1 in there, it's 2 minus -1. It's 2 plus 1. I'm going to have a maximum equal to 3 at some angle. When is cosine going to be -1? 180 degrees. Over there on the left-hand side of the graph, 180 degrees. Find the other two. Find what the maximum value is. Find where that's going to happen. Lester, what was your maximum on that one? 1 plus 3 sine theta?
I had 4.
You had 4 because what'd you want sine to be then? 1. You wanted sine to be 1. That's going to get him a maximum of 4. Brett, when is that going to get you a maximum of 4? At 90 degrees, because that's when sine is 1 at 90 degrees. Good. The next one, 2 minus 5 times something. Amanda, what's the biggest number we can get there? Yep, you'd want to plug -1 in there, and if you plugged in -1, your maximum is going to be maximum of 7. Alyssa, when is she going to get that maximum of 7? At 270 degrees, because that's when sine is -1. Everybody clear on those things? Now we're going to take all of that building blocks, and we're going to actually make the graph now. All right, so it takes a second to build there, but now that we've got that, let's do it. 2 plus 2 sine theta, our job is to graph that thing. Start off by finding what type of graph it is, what type of symmetry is it going to have, and where's that maximum value. Take a second and fill those in. Zach, what type of graph is this guy going to be? This one is a cardioid, and so he knows. Why did you know it was a cardioid? Numbers are the same. Leading coefficients are the same. Aisha, what type of symmetry is this thing going to have? Y-axis symmetry. It's a sine graph, and so sine graphs on a polar graph is going to have y-axis symmetry. Maximum. Gracie, what's my maximum value that I can get here? 4. She's answering the question 2 plus 2 times what? She would want that to be a 1, so the maximum is going to be a 4. Where is that going to happen? At 90 degrees, because she's trying to figure out when is sine going to be 1. That's at 90 degrees. And so we are going to put this on a graph now. We know a point on our graph. We know the point is 490. Okay, that is a maximum value, 490. I'm going to put that dot right there. That's the first ordered pair that I have here. No point in this graph am I going to ever have an R value that's bigger than 4. That's the biggest one we could come up with. That's why we call it the maximum. We are then going to fill in the rest of this circle. The good news is we're going to make it easy on ourselves. All right? Aisha told us that we had y-axis symmetry. And so if we have y-axis symmetry, we don't need to find all of those values. We only need to find half of those values. Because if I know half, I can do the rest. So which half, show me with your hands, which way would you want to fold this graph in order to have the correct symmetry? Y-axis symmetry. We're folding it hot dog style over the y-axis. And so what that means is if I know these values over here, if I know all of these values over here and I take them and folded them over the y-axis, it will match the picture. Anybody agree with me? Wonderful. Let's do it. And so we are answering the question. 2 plus 2 sine theta. And so I want to plug in different sine values here to figure this out. And we're going to make it easy on ourselves. We started right here. Right here at 90 degrees. I'm going to work around the left-hand side of this unit circle. Or the right-hand side, whatever way you're facing. At 60 degrees, 2 plus 2 times sine of theta. What is sine of theta going to be at 60 degrees? square root of 3 over 2. And so if I did 2 plus 2 square root of 3 over times square root of 3 over 2, is that a fun number? I don't want to deal with it. The answer would be 2 plus radical 3, so it's like 3.7 something. No one wants to graph that. We're going to skip it. Okay? At 45 degrees, do you want to do sine at 45 degrees? No, because it's radical 2. We're going to skip it. Not that it's not a good number, but in order to sketch it by hand, we're going to pick some better values. What about at 30 degrees? What is sine at 30 degrees going to get me? A half. And so by skipping down here to 30 degrees, now we got a good number. I'm plugging a half in for sine. Carrington, if I'm plugging a half in for sine, what's my radius going to be at 30 degrees? Yep, 3. 2 times, I thought you said 2 times a half is 1 times, or plus 2 is 3. So at 30 degrees, we have the ordered pair of 3 30 degrees. We picked a good number. Not that the other ones weren't good, but they were ugly, and we didn't really want to deal with them. What's the next angle we would want to use here? 0 degrees. Let's look at 0 degrees. If I went to 0 degrees, it's 2 plus 2 times sine at 0 degrees. Sine at 0 would be 0, and so my radius is going to be 2. 0 degrees, I got a dot at 2. And I would keep going. Find 2 more ordered pairs on that half the circle that you can graph. Courtney, what other angle did we use? So we used 270 because sine was -1 to get me 0. At 330, if you use 330 degrees, hang on, let me graph that dot. 270 was 0, and then at 330, it's 2 plus 2 times -1/2, and so that would get you 1. So at 330, we got the ordered pair of 1, or we got the radius of 1. Cool. There's my dots. It looks not like anything yet, but this graph has y-axis symmetry. So if it has y-axis symmetry, any dot on the one side of the graph could be folded over and match up with the other side. So that's why I like using colors here, because I can match them up. This dot here is going to fold over and be that dot right there on this side. All right, the 2 in the middle, the purple and the orange one, are going to stay in the same spot because they're on the y-axis already. That dot can fold over to there. That dot can fold over to there. There are my points. Looks still kind of ugly. Let's just use our calculator to give us a better concept of what's happening here. I'm hitting the y equals button. I'm going to type in those numbers. And so this one was 2 plus 2 sine theta. If you're not in polar mode, make sure you've put your calculator in polar mode. 2 plus 2 sine theta. And look at this shape here as I type this in. Everybody look at the screen for a second. Try to find out, my computer goes faster than your calculator, but try to figure out where it starts to graph this thing. It did it really fast. Where did it start on your calculator? Where did it start? On the right, it started at 0 degrees. It started right here at 0 degrees, and then it worked its way around and back to there. All right, but it's always going to start at 0 degrees. That's where my graph's going to start, at 0, and kind of graph its way around. You don't have to do that as you do your picture, but understand where it's beginning. It would start at 0 and work around. We're going to then connect the dots. If I were to start at 0 degrees, it would have looked like this. It's not the prettiest graph in the world. We struggle with graphing circles, so graphing these things is not going to be easier all of a sudden, but there in general is my shape. Questions on how we made a cardioid? Let's flip it over to the backside. We'll go a lot quicker on this next one. We've got the basic idea. Let's see how this works. Fill in the top part with what you can and start thinking about the next part. You're filling out the top part. Where's the maximum going to be? What is the symmetry? What type of graph is it? Do that real quick with your neighbor. Mackenzie, what type of graph is this one going to be? Limassol. Limassol with a loop. Good. Limassol with a loop Think of it like an S in there, and it does the right thing. Limassol with a loop. Again, it's because her leading coefficient was bigger than the number we were adding to it. Hannah, what's my symmetry going to be? X-axis. And so if it's x-axis symmetry, think of the letter C, and that it would be able to be folded over here. Cole, what's my maximum value going to be? 5. He's answering the question 1 minus 4 times what? What number would you want to put in there? -1. That would get you 5. And so when is cosine, because it's a cosine graph, when is cosine going to get you -1? 180 degrees. And so we've got a point on this graph. 5, 180 is an ordered pair. 5, 180. And so that's the biggest number we're going to possibly get, and we're going to work from there. This has x-axis symmetry. So which half of this graph do I want to learn in order to fold over and get me the other half? The top. You could say the bottom. It doesn't matter. But one of the vertical halves is what I'm going to work with. And so I'm going to go around my unit circle, and I'm going to find these values right here. Because if I find those values right there, it's going to help me to make my whole graph. Again, I'm plugging into that 1 minus 4 cosine theta lookout. 150 degrees. Do we want to do cosine at 150? Nah, it's radical 3. I don't want to deal with that. 135? No, radical 2. 120? Sure, at 120, cosine is -1/2. And so at 120 degrees, what is my radius going to be? 1 plus 2, it would be 3. So 123, graph 3 more dots there on the top half of that unit circle. You can keep working. I'm going to go quick here. The next one I'm going to use is 90 degrees. If I use 90 degrees, it's 1 minus 4 times 0, because cosine here at 90 degrees is 0. So my radius is 1. 90 degrees is 1. Then I could do I could do 60 degrees. At 60 degrees, it would be 1 minus 4 times 1/2. So 1 minus 2, that would get me -1. How do I graph 60 degrees -1? Ride the line. 61 is here. I'm going to ride the line across. Now I'm down there. There's -1. And then my last dot would be 1 minus 4 times +1. I would want to use 0 degrees. At 0 degrees, it'd be 1 minus 4. And so my radius would be -3. Here is 0 degrees, +3 right here. I'm doing -3, and so I'm riding the line across to the other side. This graph has x-axis symmetry, so we're going to fold over the x-axis. I don't really care where the dot was. I'm going to graph it over the top of it and have them match up. And so this black dot that was here at 3, 120 is going to match up with 240 down here at 3. And this pink dot that's down up here at 91 is going to fold down to -90. And this other dot, we'll call it coral, we'll flip that up and it goes there. And then the purple and the blue one that were on the axis are going to stay on the axis. There are my dots. It's weird to see, all right? Right now it might not make a lot of sense. That's why we're going to use our calculator to get a better picture of this. So I turned on my old calculator because my old calculator graphs slower. So if I hit the y equals button, yeah, we'll just go with this. Okay, sorry. If I hit the graph button, let's see what happens. You can see where it began. See how it kind of rolls its way through? Where did it start to make my graph? The one that was 0 degrees. And where is 0 degrees? What color dot up here is 0 degrees? The blue one. I started here, and then I wrapped my way around. The next dot was this 60-degree dot, which is this one down here at 240 degrees. That's the why it's making the picture the way it did. So I'm going to try to connect my dots in the way it did it. You don't have to do it in the same order, but it's good if you do. We're going there. We're going around to the outside, around the outside, back around, and through to the middle. It makes you that shape right there. However you want to graph it, graph it. All right, I'm pretty good at these. I've done them a lot, so I know where to connect the dots through, but use your calculator as a guide to go through those. Questions on how I made that shape? What if I asked you this? What if we graphed 360 degrees? What if I asked you to graph that shape for 720 degrees or 4 pi? You went around 2 times. How would this shape look different? How would it look different if I asked you to start at 0 and go all the way to 720 degrees? It would look exactly the same because as I go around, it would repeat and do the same dots. Would it make sense that it would look different if I said just graph it from 0 to 180 degrees? Yeah, it would be half of that shape. All right, that is something that you use in Calc BC. So next year, you're going to talk about graphing a certain portion of that, and we'll continue with that tomorrow. See, I know